Hey everybody, this is Justin with Top Tier Math, and we finally got the geometry final review done. So just two more for high school math for pre-calc and calculus. I know it's been like a year and a half since the last one came out. It won't take that long for the other two, but if you're new to these final reviews, what I do is I go through the Regents exams. They don't have one for the other two classes, but we already have one for Algebra 1, Algebra 2. I wanted to get geometry out sooner so that you could have it before your final. But if you haven't done them before, basically, I put a link in the description to the actual test. Make sure you take the test. And then I put a link to the answers. So go check your answers, figure out which ones you got wrong. And I put timestamps on each of the parts. There's a three videos for this particular final. And you can actually click on the timestamps for every single question. It'll take you right to that question. Each of those questions will have a link to some extra practice problems so that you can go and make sure that you feel comfortable with whatever the topic is. That's pretty much how these ones go. Hopefully you guys can find it helpful, and it's not too late in the year, but I wish I could have gotten out sooner. Work just kind of got away from me with the new job, but hopefully to keep these ones going, and hopefully you find it helpful. So with that being said, let's go ahead and get started. For number one, it looks like we're trying to find the measure of angle ABC, and we're given a couple of angle measures, and we're also given that these two lines, FAD, FAD, and EHC are parallel. So I'm going to go ahead and mark those just as a good, rule of thumb. Make sure you mark all your givens. So I'm going to put these here as well. We know FAB right here is 48 degrees. And then they tell us ECB, which is ECB, that's right here, that's 18 degrees. Now from here, obviously you're probably thinking we're probably going to use that parallel line. And if you remember, one of the biggest things that probably the first thing you learned about with parallel lines and angles is that alternate interior angles are congruent if the lines are parallel. And if you look, FAH, and there's multiple ways to say this one, CHA or AHC, those are alternate interior angles. So those must be congruent. That means this must be congruent to this. So we know that, and that's helpful because if you look, this 48 degrees, that's an 8. This 48 degrees, that looks like a clover. Let's try that again. 48 degrees is we've got two angles of a triangle, and we're looking for ABC. We're looking for this. I'm going to change colors a bit. We're looking for that right there. So my tablet's being really slow today. Let's try this again. There we go. Okay, so we're looking for that. And there's a couple ways to do this. What I'm going to show you is, because this is something you definitely need to memorize, is what's called the exterior angle theorem. You need to memorize that. You've probably seen it, maybe not by the name, but you do need to know what it is. And basically it says if I add up any two interior angles of a triangle, it will add, that sum will be congruent to the exterior angle of the third, the unused angle. So if you look, this is tempting to call this angle B. Don't do that. It's this angle right here is actually HBC or CBH. If you and I add up these two angles, they should add to the exterior angle of this third angle. So this angle right here. And you and I can do that quite easily. 48 plus 18, that's just 66. That's exactly what this angle is because of the exterior angle theorem. Now, if you didn't remember that, and you will need to remember that because there's some questions where you can really, if I'm not mistaken, you can only answer them if you know that. You could have done it without it. You could have said, all right, well, I know all triangles add up to 180. We could have added these up, and to get angle this, whatever x, we'll call that. To get angle x, we could add up to 180, subtract this 66, and we would have gotten, I think, 114. And then if you look, angle x plus angle question mark are I can't even think of the word, a linear pair. So they're supplementary. They add up to 180. So we would have just done 180 minus 114 anyway, and we would have gotten 66. But that's more work. That's more work than you need to do. You want to make sure you remember this because it will help you in the long run. You're definitely going to see it on the exam. So long story short, the quick way, if you notice and you recognize, hey, we got a triangle, this is the exterior angle of that triangle, I can add up those two angles and get that exterior angle really quickly using this theorem. Okay, so that's pretty much it for that. I don't want to, pigeonhole it and say, hey, this is the only way that you can do it. There's sometimes other ways to do it, but you have to memorize this formula because it will pop up. Okay. So number two, we're trying to find the height of a cone given its volume, and we also know the has a base diameter of 12. So we already know the volume. Usually they're asking you to find the volume, but we're going backwards. So I gave you the formula for the volume of a cone down here. This is definitely super important. If you notice, it's actually just the volume of a cylinder divided by 3, multiplied by 1/3, right? So that's kind of convenient. But basically, we just kind of see what we have. Really, we know that the volume of the cone they give us, so it's 108 pi equals 1/3 pi, and then the radius, well, if the diameter is 12, remember radius is just half of that, so the radius squared, that's the radius is 6, so squared, so times 36, and then we have our height. 36, there's multiple ways you could do this. You could say 36 divided by 3 is just 12, so we could kind of make that a little bit prettier, and then we could divide by 12 over here. We would get, well, actually we could divide by pi. Let me move this h over, so we can get rid of the pi. That's gone. On the right side, left side, that cancels out, and we know that 12 times the height is equal to 108. Excuse me. So if we just divide by 12, we end up with the height being 9. 9 doesn't look like there's any units. I didn't see any up here, but just in case you do a free response question, make sure you put whatever the units are there. Okay, and that's pretty much it for that one. Make sure you memorize this. They might give you the formula for that on the final exam, but just in case, you make sure you know that, and be super careful that you don't plug in 12 for the radius. That gets a lot of people. Okay, so we've got two triangles, JGR and MST, that are similar. If you remember, polygons that are similar just means that corresponding angles are congruent and corresponding sides are proportional. Now, if you notice, every single answer choice here is all talking about angles, so that's probably what we're going to focus on. And if you look, we want to know which is not true. So let's take a look at one. Remember, corresponding just basically means what's in the same spot. And I like to teach students, look at the letters. The first letter here is J, the first letter here is M. J is congruent to M. Sorry, J is corresponding to M. So angle J should be corresponding and congruent to angle M. So those are congruent. So that has to be true. So that can't be our answer because it's not true. So if you look at 2, angle G is congruent to angle T. So if you look here, here's G. It's on the right side. That would be congruent to angle S. If you look, G is in the middle, S is in the middle. Those are corresponding. Those would be congruent. Actually, so 4 is true, but we want to know which one's not true. And just to drive the point home, R and T, R is on the left side, angle T is on the left side, and they also, again, R is the third letter, T is the third letter, so those are both corresponding to each other. So because those are all true statements, the only one that doesn't make any sense is 2, because G and T are not corresponding angles. Therefore, it's not always true. Now, they could be true, but it doesn't mean they're not necessarily true, right? So it doesn't have to be true. All right, so we want to prove or figure out which statement proves that parallelogram ABCD is a rectangle. So just to go through these quickly, because I know there's a lot. It's kind of, these questions are always kind of weird, but just so you know, so AC being perpendicular to BD. So AC is here, BD is here. That's saying that the diagonals are perpendicular to each other. That doesn't prove that it's a rectangle. It could be a rhombus. Rhombi, is that parallel or plural? I don't know. Rhombuses have diagonals that bisect each other, so this does not automatically mean it's a rectangle. Now, AC bisecting angle BCD, that could be a rectangle, but it's not. It doesn't prove it, right? Again, that could be a rhombus as well. And then if you look at 2, AB, this one's weird. AB being perpendicular to BD, that makes no sense. There's no way that these guys would ever be perpendicular. It just wouldn't work out. It would be like a non-existent shape, which I don't know if that makes any sense, but that definitely couldn't be that. But just so you know, for a rectangle, our definition of that I want you to be very comfortable with is that a rectangle has 4 right angles. Now, you can't really tell by the way that I drew it, but 4 right angles, and that diagonals are congruent. That's what defines a rectangle. And then obviously we have a special kind of rectangle called a square, where the diagonals do actually bisect each other, but that doesn't automatically mean that 3 is correct. Okay, but number 1, if we know it's a parallelogram and we know that the diagonals are congruent, then automatically we know that that proves it's a rectangle. Okay, so number 1 for that one. All right, so for number 5, what we're doing is it asks us to find endpoints of a line segment PQ that has 2 particular coordinates. And I've gone ahead and drawn out coordinate P and coordinate Q on here. That corresponds to these two up here. And we want to find the coordinate of a particular point A that's going to be on this line, on line segment PQ, that divides PQ into a ratio of 1 to 3. Now, when I first saw a problem like this back in the day, I was like, what in the world is this? This is called partitioning line segments in geometry. Okay, that's what this whole topic is about. So basically, here's the best way that we can go about solving this. I want you to break up the distance between our two coordinate points into the vertical distance. Let me see if I can draw this right. Vertical distance and the horizontal distance. Let's make that a straight line. Let's try that one more time. There we go. All right, so the vertical distance from P to Q, that looks like, what is that, 5, 6, 7, 8? And then the horizontal distance between P and Q is from -7 to 5, that's 12. Now, the line A is going to cut that into a particular fraction. Wherever we put this point A, I think I said line A, point A is going to divide PQ into a particular fractional part, all right? And that part is 1 to 3. So imagine if I drew a rectangle, and I put a point right here, and let's say here and here. Now imagine these were all the same size, and then here was 1. That's kind of like the 1 to 3 ratio. Now imagine that as a fraction. This 1 takes up 1/4. Okay, so that's the fraction that we're going to use to break this up so that the length of wherever we put A, let's say we put it like right here. This part right here, this length is going to be 1/4 of the entire line. And how we can do that in a shorter way so you don't have to draw a rectangle every time is you can just add these two numbers together. 1 plus 3 is 4. That's our denominator. And then in this case, 1 is going to be our numerator. And that's because we're starting from P. If we started from Q, we would take the 3, and wherever we put A would be 3/4. It would still give us the same point, but we would start from Q instead. Now, it's a lot of talk. Let me go ahead and actually show you what we do with this fraction. All we have to do, now that we have these lengths, we can take them and multiply it by our new factor. Each length is now going to be 1/4 of the original length, and that's going to give us A. Let me see if I can get rid of this line here. There we go. So we'll take 8. 8 times 1/4, that's the same thing as 8 divided by 4. That's going to be 2. So I'm going to start at P, and I'm going to go up 2 units now instead of 8. So I go up 2. And I'm going to take 12 and take 1/4 of that. That's the same thing as 12 divided by 4. Now I'm going to move over 3 instead of 12. So 1, 2, 3. Luckily, I drew this line so that it just happens to perfectly, it better be on the line. But that right there, that's our point A. Point A is right there. And it looks like that's, what, 1, 2, 3, 4, 4, -3. That's a comma. But 4, -3. That's all you do for these ones. And I think it's the best way to do it because you just basically figure out what's the vertical and the horizontal distance, take this ratio, turn it into a fraction. And in this case, the reason that I started from P was because it says it divides PQ into a ratio. So that tells us we want to start at P because that's the first letter. Okay. Now again, we could have done 3/4 instead, and we would have started from here and gone and ended up at the same point. But that's the best way we want to do this. Get your fraction, get the vertical horizontal distances between the two coordinate points that they give you, multiply those distances by that fraction, and then start from the starting point and go up and over whatever you found. So I found we go up 2 and right 3 instead. And that's 1/4 of the original distance, and that's exactly how we get 4, -3. Oh, I said 4, sorry. If you guys probably already caught this. That's -4 because we're going to the left. -4, -3, and that should give us answer 4 for that one. So again, if you're not comfortable with that, usually seeing it one time, it's not like, oh, that makes perfect sense. But I found this is the best way and quickest way to do it, even if you don't draw a graph, just to take the coordinate points and figure out what's the distance between them vertically and horizontally, and then multiply them by your fraction that you get from the ratio. Okay, so again, if you want more practice with that, that's called partitioning line segments, and it's about as fun as it sounds. But that's how we go about solving those. Alright, so for number 6, we're given a trapezoid, and this is super important. Anytime they give you something like this where it says, alright, line segment AB is parallel, that's what that is, parallel to line segment CD, I always recommend writing that on the diagram just so you know, and you don't forget. So let's go ahead and write what they give us. We have a couple of lengths here, a few lengths. So they tell us AE is 5.2. They tell us AC, so this whole thing, is 11.7. So I'll just kind of we'll just do this and make an arrow to that. 11.7. And let's try that again. 11.7. There we go. And CD is 10.5. What's the length of AB? So we're looking for this up here. Now, one of the important things to recognize is, like, if you look at this, it's like, wow, I don't know, there's literally a bunch of stuff going on here. But if they give you parallel lines, it's almost a dead giveaway. We're probably going to be using some sort of alternate interior angles or same side interior or something like that. So what I want you to be comfortable with is, because these are parallel and we have this AC that's acting as a transversal, if you remember your alternate interior angle theorem, which you need to know 100%, you need to know all those theorems that have to do with parallel lines. This angle right here is alternate and interior to this angle here, and because these lines are parallel, they're congruent. Okay, now the same thing would hold true for this angle and this angle. Those are also alternate interior. And right off the bat, that's all we need to know, that these two triangles right here, DEC and BEA, are similar. So all the angles are not only congruent, but corresponding sides are similar. So the corresponding sides don't have to be congruent, but they are similar, meaning there's some sort of proportion that we can create between them. So let's do that. If you can imagine, AE is corresponding to EC. And we have to, so obviously we need EC. A lot of people are going to use 11.7, but that's the entire AC. So to get that, we just subtract the 2. And totally can't do that off the top of my head for some reason. Blanking out. So let's figure out what that is. 6.5. Some of you can do that real quick. 6.5. So now I'm going to write this EC as 6.5. Now, what we're looking for is this. I'll put this as X. We're looking for the length of AB. And because we know that these triangles are similar, we can create a proportion. There's multiple ways that we can write this proportion, but let's do this. I like to put the corresponding sides of the opposite triangles as numerator and the denominator. So 5.2, that's going to be the smaller side because it's smaller than that. 5.2 divided by its corresponding side, that's a 5, on the other triangle, is equal to, now we started with the small triangle, so we're going to do the same thing, equals X over its corresponding side in the other triangle. So this side down here that we happen to know. Okay, and if you go ahead and you multiply 5.2, so if you're at this point and you're not sure what to do, you want to make sure to go back and double check cross multiplication. That's something that you should definitely know how to do. But if we go ahead and we solve for X, we should get, using a calculator, that when we cross multiply that, we should get, and solve for X, we should get 8.4. So 5.2 times 10.5 divided by 6.5, and that gives us that 8.4. Okay, so this is purely a question of how comfortable are you with parallel lines, alternate interior angles, but also you had to be comfortable with the idea like, oh, wait a minute, because of that angle-angle similarity theorem, that's something you should definitely know as well. It usually looks like this. Angle-angle similarity theorem is a way that you can prove that two triangles are similar, something that you have to know, 100%. If we can prove that two triangles are similar, then we can use the proportion if we have enough information of the sides, which we do in this case. We have 3, we're looking for the 4th, that's enough to set up a proportion. And this is not the only way that I could have written a proportion. There's multiple other ways that we could write it. This is just the way that I prefer to write that. Go from one triangle to the other, and then do the same thing with the other side of the equation and cross multiply. Okay, so that's what that is. If you're not comfortable with parallel lines or those theorems, make sure you go back and double check them. Alternate interior angles, corresponding angles, that's 100% something that you will definitely need to memorize. And I think there's 5 of them, if I'm not mistaken. But when you get a little practice with them, they'll become like second nature to you, I promise. And I'll put some links in the description below so you get a little bit more practice with those and all that fun stuff. But that's all we need to do for this one. All right, so for number 7, it looks like we're given 2 right triangles, and in the question, we know that they're similar. All right, so that's super important. That's something obviously we're probably going to need to know. They tell us we have right angles at B and E, and they give us the line segment lengths of BC and AC written right here, and we want to know the measure of F. Now, if you notice, they give us all the stuff for this triangle and nothing over here. So we're looking for angle F. Now, here's where this is super important, okay? So if we know that these 2 triangles are similar, again, this all comes down to the idea of similarity, and you need to be comfortable with what it means if 2 shapes are similar. It means that corresponding angles are congruent and corresponding side lengths are proportional. They could be equal or congruent, but they're proportional. That's the main takeaway for that. So corresponding angles are congruent, corresponding sides are proportional. So with this one, if we're looking for this particular angle, we want to figure out, okay, well, what's its corresponding angle on this side, because it's going to be congruent to that. And if we can find that, then we know what F is, angle F. So if you look, the best way that I like to do this, if you're not really comfortable looking at the triangle, if you look, the corresponding angles are going to be in the same position. So angle F is the third letter in this triangle definition. So the third letter in this triangle is C. So angle C and angle F are corresponding, and because they're similar triangles, they're congruent. So if we can find the measure of angle C, we can find the measure of angle F. So let's do that. Now, if you look over here, you're probably thinking, SOHCAHTOA, something like that. And you're absolutely right. We're going to use something like that. And if you look for angle C, 15 is the adjacent. This side is opposite, so we're not using that. And obviously, this is the hypotenuse. The side length that's across from the right angle is always the hypotenuse in a triangle. So we've got the adjacent side and the hypotenuse. That's cosine. If you remember your SOHCAHTOA, adjacent hypotenuse. So cosine is equal to, let me put cosine of C is equal to adjacent, which is 15, over the hypotenuse. Now that's great. That gives us cosine, but we're not looking for cosine. We want to actually find C. So if you remember, to find the actual angle measure, we use the opposite. So depending on your calculator, you'll either see it like this, and this is not the same thing as writing 1 over cosine, like the exponent properties for negative exponents, not the same thing. That means inverse of cosine. Or you probably have seen it written as arc cosine, ARC cosine. Both of those are the same thing. So if you plug into your calculator, you'll obviously need that here. We can't do this in our head, but if you plug this in, arc cosine of 15 divided by 17, make sure you're set to degrees. If you're in radians, you're going to get some random decimal. If it's set to degrees, you should get 28 degrees. So this problem is purely, okay, how comfortable are you with similar triangles in this case? And then what do we need to do to actually find the angle? And that has to do with, okay, well, first you can set this up. You don't even have to really set this up if you are comfortable with what it means to find the angle measure. But that's all we're doing here. We're using a little bit of trig, and then we just have to use the inverse cosine. So we're doing some inverse trigonometry to actually get the angle measure, not just the cosine of the angle measure. Okay, and that's all we need to know for this one. Number 8, we have a line that's represented by this particular equation. They tell us it's dilated by a factor of k, scale factor of k, so that the image of the line is this. What's the scale factor? All right, so it would kind of help if we could get these in the same format. I'm just going to put them in standard form. No, not standard form. Slope-intercept form. So to get that, we just want to get y by itself. So for that first one, I'm just going to divide everything by 2. And for the first equation, we'll get y equals x over 2 plus 4. For this one, I'm just going to bring over the negative 1/2 x. So I'm going to add that, and we'll get positive 1/2 x plus 2. Now, you could probably take a guess here, and I'll write these, actually, they're the same. This 1/2 x is the same thing as me writing x divided by 2. So if you look, really, really similar. This first graph, just so we can see what it looks like, has a y-intercept at 4, and it's going up 1 over 2, has a slope of 1/2. I can't think of the word. Slope of 1/2. Here's a little line segment for that. Here's this one right here. Same exact thing, has the same slope, but now it's got a y-intercept of 2, and we're going up 1 and over 2 because they have the same slope of 1/2. Now, if you look, you could probably take a guess. We're going from this line to this line, and they're saying basically, what did I have to multiply by centered at the origin, dilate the scale factor centered at the origin, that's the important part, to get this new line. And if you look, well, if I'm going from 4 to 2, I divided by 2, or I multiplied by 1/2. Okay, so that would be 1. Now, the important thing here is that it's centered at the origin. If it was centered anywhere else that's not the origin, it would be a different method that we would go about solving this. But basically what that's saying is all the distances of these points from the origin of the original line are now half of the distance on the new line. And the easiest one that I want you to pick, I don't even want you to pick any others, just pick the y-intercepts, because you can easily see, oh, okay, well, from 4 to 2, all right, that's divided by 2, or multiplying by 1/2. Boom, there's our scale factor. Okay, so that's all we're doing for this one. And again, I I would double check if you're not comfortable with this about what it means to dilate. So dilation, your function transformations, dilation is part of them, translations, all that fun stuff. But a really nice way to do this is to, one, get these in the same format. So put them in slope-intercept form, and it just makes it easier to see, like, oh, okay, well, from 4 to 2 divided by 2. But it won't always be that easy, but it makes it a lot easier to read moving forward. But this one was purely just how comfortable are you dilating. Even though it's an equation, the same idea persists as if when you had, a triangle that was, dilated and it looks like this now, something like that. Same idea, we can do that with equations, and that's all we're doing for this one.